Okay, so let me so I ask you give a little bit of a presentation, okay, let's start. Pekka Varis from Texas Instruments, with some background in networking also outside before joining TI. So I was going to give a little bit of a talk at the kind of the requirements or a use case level on a kind of a trendy topic of time-sensitive networking, so just to set the expectation. So it's kind of describing the use case, not trying to propose that this is the solution to build. I'm kind of looking for the I guess the folks in this room, and then in general to see if Lenaro is interested in picking up on this and sort of coming up with solutions. So it's kind of a mix between okay, let's see what it's a mix between. Okay, so what is time-sensitive networking? Most people are probably familiar with Ethernet AVB, or audio-video over Ethernet from about over 10 years ago, which was kind of an okay solution. The example pictures, I guess, make it more concrete. So the middle picture here is a audio-video mixer, not Ethernet AVB. So each individual cable is an individual stream. So you can imagine that that's a lot of cables, a big mess. So replace it with one big fat Ethernet, and the world is good. That's kind of the motivation, and that's of course a very clean and elegant setup. It doesn't mean it all look that clean. Okay, so then sort of at the same time in the automotive world, of course, people are using their CAN buses and so on. It's not using Ethernet, and then in the industrial market, they kind of moved over from proprietary serial bus-based proprietary networks to Ethernets that were a little bit hacked up in one way or another, and they were either like EtherCATs or Profinets or anyway, kind of variations of Ethernet in one way or another. Okay, so what's happened is kind of the AVB version 2 or is where the interest of these kind of three domains kind of started to merge. That the automotive guys and industrial guys sort of noticed that, okay, Ethernet is winning everywhere, so how can we jump on board and get all the goodness of Ethernet, but we still want our guaranteed delivery type features. Okay, so most of the TSN is related to Ethernet MAC layer, but there's a few items which I believe at least show up in the software, and I'll kind of migrate towards that part. Yeah, and then here's a pointer to an excellent presentation for an introduction on kind of all angles of TSN. It's by University of New Hampshire, so it's kind of neutral, and it's a nice description of 25 slides on standardization bodies and various consortiums who are involved, and then kind of like what are they trying to solve, and then the end part of it is how it's being solved. So that's an excellent presentation. So I've stolen a whole bunch from there, so just gave credit to Bob Noseworthy. So this is then the kind of the hardware-centric view of what is time-sensitive networking. Well, in reality, it's a bunch of IEEE standards. They're just bundled into this, I don't know, semi-fuzzy TSN. So what exactly is it? Do you implement all of these and so on? That's not really, I don't think that's defined. So you can do time-sensitive networking and only do like 3 of these. At least in my understanding, some people might still call it TSN. So, okay, so if just without digging too deep, just describe it. So the first thing to solve is, of course, you got to make everyone have the common agreement of time. You can do it by putting a dedicated wire to distribute a clock. Of course, that'll work. Or you do it with a conveyor belt, like with an old factory. I mean, everyone's on the same time if the conveyor belt is your everything's moving with the belt. So time synchronization has to be solved. Of course, time synchronization needs to be solved for other reasons as well, so that's not necessarily unique to TSN. Okay, then there's a bunch of, I think the next 4, there's QAVs and QBBs, there's a queuing model where really the unique new stuff, I would say, are the time-aware queuing or time-aware shaper and frame preemption. So let me just kind of focus on those a little bit here. So the time-aware queuing is basically, in an ugly way, if you said it's TDM over Ethernet. So they're recreating TDM over Ethernet, and if you look at it, it actually kind of goes to the level that I think some of the people involved in the standardization are the same people that did it in ATM. So it's kind of a back to ATM, but just over Ethernet, which is not necessarily a bad thing. And I don't think it's And then they do have included now approved it's frame preemption in Ethernet. So frames larger than I think 128 bytes. There is a true frame preemption and continue after preempting, so that the best ever traffic can send their jumbo frames or 1500 frames, while the real-time traffic gets their little packets in their time slots through. Okay. Okay. Then there's a couple. Okay, redundancy comes into play as well, of kind of indirectly, but it's also not just time-sensitive networking, but usually redundancy matters in TSN as well. Okay, and at the end there, the second from last, they had to get the preemption going, you got to touch the lower levels of Ethernet, so that's included. So touching but but all that's approved, so it's no longer like a unique branch, it's standard Ethernet. Okay. A little bit more on the motivation, so it's pretty broad. I talked about this, but now I just listed a bunch of companies to kind of generate that, okay, this is something that it has a broad set of interest. If I listed some company, they're not endorsing me listing them, or I'm not saying they are really good at this, but I've just, that in a public forum you can find in the kind of the consumer audio video contributions or conference presentations by Broadcom, Intel, Apple's, some of the, they support some of the advanced features in some of the MacBooks, and people have kind of referenced those. On the professional audio video side, they have if you look, you'll find some pretty, there's a very nice example of the ESPN's, for those who are not from the US, that's the big sports channel. So their main center on the East Coast in Bristol is called DC2. It's built from scratch. It's Ethernet AVP across the board, like a couple $100 million worth of stuff. Sports Center comes from there, so they're promoting it as an example, and there are these professional Riedel, Harman, and other professional audio video guys, and Cisco, of course. Cisco is in many of these domains, but for example in that domain they've shown up. The car world, it's everything from the driver assist, infotainment, chassis control, powertrain, body. So today there are kind of different technologies for different. If you open the windows, it doesn't go over the same bus as if you engage the emergency braking. In the future, it might. So they're both the end producers like Audi and BMW, and then these massive kind of the technology providers like Continental, and then the semiconductor guys like us and Broadcom are active on, and the industrial side, all the big names are there. So basically nobody's missing. That's kind of, I guess, what I'm trying to say. Okay, Then going a little bit to why should Linaro care? Well, it's this is and why it's Linux networking. ARM is dominant. This stuff is kind of some of it is very old, so it's kind of predates the dominance of ARM. So a lot of people are looking at migrating to ARM. And it's at the same time, it's RTOS all over the place, or even bare metal. But if you built your serial port-based communication mechanism in the 80s, you might have used serial port. Now you're finally upgrading. You're looking at Linux at the same time. So I got this. I got to update my networking, and I got to update my OS. Seems like a good intersection with what Linaro is doing. The IoT or industrial IoT, Industry 4.0 in Germany, whatever you want to call it, I think the one unifying thing there is they want the full connectivity and security. So, and the easiest way to get there is just put Linux there and run your full-blown stacks the same there. Don't try to go squeeze it into a microcontroller. I mean, the Zephyr stuff is all fine, but an easy way to get to a full-featured connectivity and update mechanisms is put in Linux. Okay, and then you also have to. This is true embedded space, so they need to be cheap. The silicon that needs to run this is it kind of needs to go down to the sensor level. That I have a sensor that the box sells for a couple $100. So the silicon that's able to do this has to fit in that budget. So nowadays you can get Linux capable ARMs. So ARM Cortex-A devices in such kind of an MCU type price range. Okay, and then all these markets also want their development cycles to accelerate. I mean, traditionally it's a new product like every 10 years or something. So now at least the management there is dreaming of like, can we move a little quicker? And then they have a whole bunch of new engineers who kind of expect better. And so there's a lot of things driving towards that. Yeah. So, okay. Then I got kind of a couple pictures just to reiterate why this is different. So this one, I took it from Michael Tiener's presentation, but it's just showing time. So we need the timing over packet to get everyone to run at the same clock. If you don't have that, forget about it. I mean, but so that's kind of basic. Timing over packet needs to be there. Then I need scheduled queues and preemption, which is the part which I think maps to the possible software implications. Because on the wire, I want it to look like this. So at these synchronized TDM instances, the black vertical line, I have agreed with the resource reservation protocol that this guy can transmit, and it's guaranteed to get a slot across the entire network. And I create these kind of what's colored red here. Is I create these kind of a TDM-like time slots in the Ethernet traffic that guarantee deterministic latency for those, typically a control traffic or a sensor traffic telling how fast the liquid is flowing. You want that going to the valve that's controlling how much liquid do I let through. So that's the small packets. But then at the same time, I want the blue on the blue stuff, which is disproportional. Of course, the blue is usually a lot larger. I want my regular Ethernet to work. So I want my whatever software update, firmware update stuff, all that traffic to just work. So how do I make these two things coexist? And how do I of course, for the switch, it's a big deal, but at the endpoint, how do I make that work? Okay. And hey, by the way, feel free to fire away questions or comments. So if something's not clear. So, yes.
You call it Ethernet, but I mean, Ethernet in my mind is very well collision.
Yes.
What's left of Ethernet when you start doing these things?
Exactly my thoughts. But I'm presenting. I have the standardization and the motivation and how it came to be. That's exactly my thought. It's no longer really Ethernet, but I view it from this use case perspective. The real-time, the guaranteed delivery use case is valid. Now, Ethernet has been hacked up to solve the problem. And because these semi-proprietary solutions deployed today have shown that yes, it works. Now the IEEE has standardized kind of a set of those. I mean, it's a little ugly to call it hacks, but it's really ATM over or token ring over Ethernet.
You say over Ethernet still, it's not Ethernet. I mean, you cannot take an Ethernet switch on today.
Okay. Yes. It has. What is addressed there is compatibility is a big deal. Of course, with a non-TSN switch in the network, you won't get the guarantees of delivery, but it will work. So they've stuck to the principle of Ethernet is the backwards compatibility. They've kept that, and that's why some of the things look so kind of weird. Is to perhaps when you go to a detail, they look weird, but the backwards compatibility is there, and it is designed in a way that even with layer 2 switches that are not aware, I can get to some types of levels of service, but the most extreme cases are always really closed networks, or like not closed networks is probably the wrong way to say, but kind of firewall bubbles. Like the easy one to think about, everyone knows what a car is. So if you think that a car has 100 sensors and a couple engines and it's an electric car, so then you kind of network that. That's a closed network. You can kind of predetermine engineer it, but it might also talk to a kind of a regular Ethernet is, yeah. But I completely agree. It's not.
And another question as well, just talking about the synchronization of these things. What kind of time do we talk about here? Are we on nanosecond levels?
Yeah. Okay. Yeah. So okay. Let me. I'll come back to that with this picture. I didn't add any numbers. And again, of course, I found a nice picture, so I didn't draw anything. So I put that's a credit from who. But I'll come back to the number after I kind of describe this picture. It's kind of cramped, but think of this part as the application. That the application is, I have the real world, and I have a computer that's trying to control it. So I gotta get readings of. The computer doesn't know anything about the real world, so I gotta get the sensors to tell me what the real world looks like. How fast is the wheel spinning? What's the air pressure? I gotta get all these readings in. Then I make decisions, and I move some actuators that affect the real world. So that's like I guess it's a cyber physical system or whatever. That, if you want to put some other fancy words, but that's my loop. But the problem is the physical processes might be over I don't know, like a factory floor. It's not just right next to the computer. So that's where how do I talk to these? So that's the application, and how tight can I make this loop? That comes to the number. Okay, so I'll get. So I think the tightest loops people run today are like about. I think there are these magic numbers of it. It's 31 microseconds for the control loop, which includes read the inputs, make decisions, modify the motion controller, like a factory robot. I think the tightest loops in commercial use today are something like that. But there's a whole bunch of systems where that is, you don't need it. 250 milliseconds is fine for the control loop. So I think where there's you don't always need to target the tightest loops, but then all these budgets of how inaccurate are my clocks, they're out of that loop. It's jitter at the transmission of an input and output side. So you kind of calculate that budget out and to guarantee the performance. So yeah. So moving on, something at least I find useful to keep in my head when thinking about in that spirit of what are they really trying to solve here, and why does it look so different. This is a typical topology here in the middle, is a daisy chain. So I got the computer up top. I got a daisy chain which is potentially 100 nodes. It's with a switch and a small computer, basically a sensor or an actuator, or maybe a couple at each node. So I have a daisy chain like this, and because maybe the physical form of the system doesn't allow me to do a star network, I'm doing a daisy chain. So then this is where that TDM kind of comes in, and these colors are trying to show it that if I agree on the transmit moments on everyone, nobody's colliding with anyone else. Everyone gets their own TDM slot, and then I'll fill the rest is usable with the traffic that doesn't meet those guarantees. Yeah, so this is just trying to draw out the flow of the packets and yeah, basically it's traffic engineered to minimize the latency, and because it's again the application, it's this guy didn't spontaneously start to transmit. By TDM multiplexing the moments, you kind of get the minimum latency to each of those hops, and here is where you can see why the preempting the frame makes a big deal, because Ethernet has the 1500, and if you use jumbo even more, but if at any of these spots a best effort 1500 comes in, it'll add up with 100 hops. So that's where they came up with the preemption. Not everyone's a fan of the preemption, so when I said earlier on that TSN is sort of these, it doesn't mean it's all of these. It does not mean everyone's going to do preemption. But at least it's standardized, so there is a possibility that you can do it. Okay. Yeah. So that was the part of the talk which is where I sort of think I know what I'm talking about. Now I'm getting to the part where it's like I'm not sure I know know as much about what I'm talking about. It's like, okay, how does this link to the Linux and kernel? So let's see. So the whole point I've been repeating all the time is there needs to be a guarantee of maximum latency. In most of these applications, average does not matter. Everything is budgeted to be always on, and very, very rarely do anyone take advantage of the average performance. So the outlier packet determines the system. Of course, that's not literally true because nothing's 100%. They always have at the next level the protocol, they'll take care of that one missing packet. But the amount of outliers has to be really, really small. Okay. So the stuff that I think is common with other use cases is definitely huge pages, the no tickless, because if I have that control loop, even if I get that one tick every 7 minutes, I don't stop the production, or I don't stop the car every 7 minutes to allow for that, or disable the emergency braking while I'm going to update some tick. So that comes into play. The RT patches, again, to get to the controlled latency. The isolation, I mean, I probably should have written it's like, usually you have a couple cores, so isolating to a given core feature so that it's truly isolated. And I threw in the PCIe pass-through as in, because in some of these systems, for example, the switch, the sensor might be talking to the switch chip using PCIe, and it might make sense to have architectures where the latency critical application is directly using the switch. Okay, I listed that there is some activity that you can easily find. So I think the first idea is to just map what's already out there, what's missing. So that's definitely makes sense. Then we've done a little bit of this kind of pre-work in the already in LNG, because some of the parts we have today, they include these hardware capabilities that are similar to some of the approved standards. Yeah, and then the bottom part here is that I wouldn't worry about starting with the worst case latency. So don't worry about the 31 microsecond loop. I mean, it's at a gigahertz processor. You got to be counting like assembly instructions to do that kind of a loop. So they'll keep using their RTOS for that. That's just fine. I think if finding a kind of a good enough solution is the point where I can get all the other goodies that running Linux gets me, not necessarily in the context of TSN. Yeah, all these products, the networking is not necessarily the primary application. Networking is there to let me talk to the sensor. The application is not networking. So good enough for the networking is actually the goal. Yeah, I guess and maybe things like Jailhouse or OpenAmp to do partitioning would kind of be the way to go, or maybe even ODP like applications. Yeah, I probably should have added. I'll add it before I upload this or add it to the slide. Yeah. Okay. Yeah. Sorry for the text-heavy slides. I was kind of yeah. Should have put big room. Should have put more pictures. So okay. So there's data plane and control and management. I split things like that. I think the control and management, somehow I don't necessarily see that as a first priority or something. It's not really that special. It's just regular control stacks. So I wouldn't make. But then on the data plane, that the transmit side, or as the specs call it, a talker. If the Ethernet hardware on board is able to do time-aware shaping and frame preemption, exposing that to the application, so that which I guess usually it's a hardware queue of some sort, or a structure, multiple structures in memory that I have I'm able to send and receive. Actually, I should have put the why. But okay, as a first step, probably the talker side, but also the receive side. How do I get this separation of when a jitter of microseconds matters? How do I? And it's all about latency. How do I get that latency value out to the application? Yeah, the preemption, because I think at least in theory that kind of could also be behind the same kind of queues if the hardware itself actually, I think even at the talker you can preempt if the best effort side was sending a 1500 packet, and now my time-aware shaper fires that I now need to send this control frame do the preemption. That kind of similar feature. Then I put in bold in the middle, testing and benchmarking. As maybe I don't think, maybe it's just me, but there's no, what if I just run the kernel stack? What kind of, with the RT patches and a few other things like that, what kind of latency profile do I get? So establishing the baseline, and then also maybe, I'm not aware of measurement techniques for, well, or I'm not aware is probably the wrong way to say it, but because it's not enough that it's logically correct. The kind of the point with the time-aware shaper is, if I'm talking, did it show up on the wire at what point of time? It's not enough that I see it ended up at the receiver, but it's like, how do I measure? How do I have that latency or the concept of time per packet? Yeah, I think that's something be great if there's a, or yeah, do you need a 300K IXIA put on the wire to measure that, or how to address that? Yeah, and then the time synchronization area, seems like there's some pretty good activity on that area already, but just because it's so fundamental, and so that'd be another one to look at, because for those, I don't know how familiar people are with timing over packet, but really the key hardware feature is a simple thing that as close to the physical wire as I can, I need to timestamp both a packet going out and a packet coming in. And now how close to the wire can I do the timestamping is, the jitter goes down the closer I can do it. So how ability to leverage the capabilities of hardware makes sense there. The software solution is inherently weaker because it's so much, the latency latency from software to wire is always higher than the timestampers, which basically sit next to the physical pin. Yeah, but there seems to be pretty good activity on that, but it's again just to map it. And then the other one here is, if you think back to my daisy chain topology, so these, if there is a small switch integrated to a device, how would that change the picture? Or would it, or would you, that would be something. Okay, and I think that's it. So fire away. Questions? Excellent.
Will the term support? Isn't it always been an IEEE standard having to do with time measurement synchronization all over these networks? I can't remember the number.
There have been, so IEEE 1588 is kind of the acronym, the number, but then there has been improvements to that in this 802.1 AS. So there have been tweaks to that done by kind of the TSN, in the TSN work. So it's nothing revolutionary, but it's tweaks to that and like convergence time and several, yeah. So in principle, it's nothing new, but it's incremental work on that side, yeah. Yep.
So is the TSN mainly focused right now on wired Ethernet, or are there also investigations for wireless?
Okay, I would say that in the theoretical standardization side, it is not restricted to wired, but in all practical drivers, the commercial drivers for that I'm aware of are restricted to wired, but you have to think of it there that it's like a lot of these areas are these ultra conservative. I mean, they just moved from a serial port to an Ethernet like 2 years ago, so it's a little too much. But yeah. So in principle, it's done in that layered IEEE manner that they should work with wireless as well. Yeah.
So back to my original questions about the performance regarding the sync you can have between different nodes of elements in this network.
Yeah.
What kind of numbers? I mean, you
Okay, so timing sync, yeah. So okay, so timing synchronization, a typical. It's also a cost trade-off, right? In the sense that if you with more expensive, usually about 100 nanoseconds between nodes is sufficient but then some systems require higher synchrony, but typically the precision timing side, what is looked for is about 100 nanosecond accuracy across the everyone. And then because that timing synchronization is then fundamental to everything else, it adds jitter to everything else because of the inaccuracies of the time. But then you just throw in a little bit more. Because again, it's looking for good enough networking. There's no value in being any better. Also, so you want the latency to be as good as is needed, but if it's any better, that's of zero value. And same with the accuracy. It's a true embedded thinking. It's not yeah. Yep. Hey, Bill. Yeah. Yeah.
So when you talk about Linux requirements for, on the networking side, does this also, come into the whole scheduler, or how do you see that?
I think so. That's a good. I would say that if we do what's been happening now, and it's kind of like if nothing is done, what happens is people will have a 2-core device. They will boot up Linux. They will do all the RT patches and core isolation. They'll put one process on the other core, try to shield everything out of it, open a window into the Ethernet hardware, and run their old school RTOS type application in that box. I think that's the default choice. And then they'll solve how do I get the regular Ethernet packets over to the Linux via some sort of a driver that takes it from the side. I think that's the solutions of today. So that's kind of where I'm bringing it up. Is that kind of? I think we could do it a little better. That's kind of, and yes, you can see some of the jailhouse. Jailhouse is already a little bit better, but it's kind of trying to look at exactly that same approach.
As I understand, the main idea is to make path from the sensor to computer as shorter as possible, right?
It's to make it shorter, but it's to make it shorter for the longest one, if it makes sense. Do you see? Because if I have 100 sensors, I need information from all of them. And there's no. I need all of it before I can start processing. Typically, they won't take advantage of. I got information earlier from these sensors. It's like I need a snapshot in time of what the physical world looks like before I can start my ladder logic to control the robot arm. So.
You can divide it from samples, for example, each second has 60 samples or 1,000 samples, and provide in each packet just sample number and synchronize all sensors of the PTP or GPS or.
Yeah. Okay. I think you're saying exactly what is time-aware shaper, kind of. I'm not sure if but I would separate it in the way that the PTP synchronization is a nice isolated feature. The only reason you need it is because I don't have a dedicated wire going to every single entity. If I have a dedicated clock going to everyone, I don't need PTP because everyone gets that same tick and everyone is completely synchronized. But in the real world, that's very expensive because you essentially need a clock cable. And so the PTP is just to replicate the clocks. So I would kind of isolate that's a good problem to solve, but it needs to be solved, and it can be solved has to be solved before any of the others make sense. So no matter how I recovered the clock, a true PTP or a true clock signal, that should not make a difference between the time-aware shaper or side.
How you are going to prototype in user space if an idea is to use Linux?
That's kind of my. Well, that's kind of what I'm. Here's the application. That's my question. What's a good way to do it? Is it because if I do it in if I just do it in Linux, because if it's good enough, people will not do these custom solutions. So what is the good enough that what kind of jitter can I get to? Can I get with a 30 microsecond jitter in Linux with RT patches? Can I get it to work? That's great. I can solve like 80% of the use cases with that, or something like that.
You will take about 20 microseconds.
Yeah, but that's kind of my first suggestion. That let's get those numbers. Yeah, where is it to start with, and with these improvements or kind of incremental things, I'll get it to this point, and what is that point? Yeah. 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 Okay, go ahead. Yeah.
So, instead of playing with the underlying Ethernet protocol, I could envision another approach, which is simply, it says, instead of doing frame creation, just set the max Ethernet frame size down to 500 or something, or make it.
Yes, and that's what some of these proprietary Ethernets. I call them proprietary Ethernet. It's probably not. It's not. This is some other word. They're niche Ethernets. They do things like that. They say that your new maximum size is 512. Now suddenly your daisy chain. They do things like that, but that is not. Yeah, and yeah. It's so that I would not get too much stuck on that preemption, because my feeling is majority of the people are not going to actually. The preemption part is rather go like what you said. The time-aware shaper, I believe, is going to, that time-aware shapers, you can't kind of get away from it. TDM over Ethernet, you're going to end up with that one way or another. But the preemption is, maybe some folks have some patents on it or something, and they're really fond of it. But, yeah. 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 But the other one, which I did not throw anything on, that the redundancy comes into the picture, and actually coming back to like the precision timing, it's actually the newer one is mixed in with the redundancy, so you use both networks, and so like so if you physically separate the two Ethernets and you do redundancy, now you got 4, and it's still, yeah, those are all valid points, and like standards are never, well, I don't think they're good, but they're never perfect, and they kind of show some interest which is not always justified, but I think at least there is a standard. So I think that's maybe better than the 7 different hacks of Ethernet that there used to be, or shipped today. TSN is really new. Most of these are approved in basically this year. So, you know. Okay. Any more questions, or I have no idea what I'm doing on time, but I'm guessing I am okay. Yeah, it's just about right. So, if there's no more questions, thanks. Hopefully it was useful. Yeah.